So let's just make up some data to practice on. Let's say that you have a couple of points, and the points are things like 1, 12, 2, 19, and 3, 25. Okay? So it'll be information like that you'll be graphing. Okay? So you may want to practice a set of numbers like that in Desmos. Or the other day we went through how to do this on the TI-84. So you may want to practice something like that on the TI-84. Are you going to have a ton of time to put the data in and get your equation out? The answer is, nah, that's not going to happen like that at all. Okay? Keep in mind that getting the equation out is just a small part of the overall problem, isn't it? Because what's going to happen is, first, when you come in Friday, okay, you already have this page. When you come in Friday, I'm going to ask you to get into your teams of 3 or 4 or whatever, and I'm going to have these cut up, and it'll be just a slip of paper about this big. You sign your names to it, and as you're then going to get 3 rubber bands, you'll get a piece of netting or a bag, you don't know which way I'm going to go, get 1 egg, and a paper clip, meter stick as well. Okay? And you start collecting data. Collecting data means you're going to take that netting, and if here's your egg, you're going to wrap the netting around the egg so that it's enclosed nicely, and then you're going to take the paper clip and run it through there, kind of like a carabiner, and wrap it through a couple of times, and ultimately what will happen is that you'll have your paper clip like this and the netting coming out like this to support the egg. Once you have something like that, loop a paper clip through, or a rubber band through there. Okay, just put it through and then loop it so that you can hold it with one rubber band and it bounces around. Okay, then you take that and with your meter stick like this, let's do this on the inches side. You start 1, 2, 3, 4. Start with the inches up at the top. Okay. Have a pen or something out this way, and then you loop the rubber band around there, and you're going to bring it up here, and you're going to hold it so that the bottom of the egg is level with the pen. And up here, you're going to hold it by the paper clip so you can get a clean release on it. Does that make sense? Now be careful, you want the bottom of the egg even with the pen, because ultimately down here, what are you going to want even with the floor? The paper clip or the bottom of the egg? Bottom of the egg. So all the measurements have to be made where it's going to be behaving the same. So if you want the bottom of the egg just barely missing the floor, then you have to have the bottom of the egg up here just entering the jump. Okay, so be careful. I've seen people do it with the paper clip there, and then all their measurements are off about this far. Well, if your measurements are off that far, what's going to happen? Nothing good, right? Okay. So you're allowed to drop it multiple times. So for example, with one rubber band, you drop it and you see how far down it comes. And you'll have some data, 1, comma, and then however far down it comes, let's say 12 inches. Then you're going to have the one rubber band on, and you loop another rubber band through to create a loop with 2 of them. So now that rubber band part's going to be twice as long. And you do several drops with 2, and you see how far down that comes. And as I mentioned the other day, you may want to use a piece of paper held out to the side. So if here's the meter stick, hold the paper like this, and when the egg just barely taps the paper, you can use that then to read, well gosh, how far down did it come? And you'll get some value there, let's say 19, and then you add the third. It's going to to take a little time, isn't it? Okay. So you're going to add the third one. Let's say it's 25. Now, it's at this point that you have some data. These are the values that you want to plug into the calculator. These are the values that you want to put in the Desmos. While one person or two are looping the next rubber band through, it might make sense to have somebody, if they're not doing anything else, to be entering the data that you just collected. And remember, the X values are the number of rubber bands, and the Y values are how far down it dropped. Does that make sense? Okay. And while you're doing this, I'm just going to come around and I have a bag or something, and you draw a little slip of paper out, and it'll say something like 5 feet 7 inches. What's that mean? That's the height you're going to jump from. Okay. So you'll get your equation. And I'm making up an equation here. Let's say y equals 7x plus 5. The x value is what? What does x represent? Number of rubber bands. What's the y value represent? Yeah, the total drop distance. Now, make sure that you do your readings in inches because the heights are measured in inches. You don't want to do part in metric and part in English. It's a good way to not do so great on the results. So do all of your measurements in inches. When you get something like 5 feet 7 inches, how many inches is that? Okay. Well, 5 feet is going to be 5. Each foot's 12 inches plus the 7. This would be 67 inches. That 67 is the drop distance that you want, isn't it? So this would give us 67 equals 7x plus 5. That would give you 62 equals 7x. Now here's where it gets interesting, because if you take 62 and divide it by 7, it's not going to be an integer answer. This is x equals 8.86. And the 8.86 is what? Inches? It's rubber bands, isn't it? Huh. So you're going to use 8 or 9 rubber bands? Ah, yeah. Here's where strategy comes in and how brave and daring you are. Yes, sir.
Would you rather have less or more?
Okay. So let's think about that. Here, let's use this string as our rubber bands. Okay? So that's too much, isn't it? So let's say I start here, and I compute that it's supposed to be, let's say that much. If I pick it up and I drop it, it doesn't hit. If I make the string a little bit longer and I drop it, well, that didn't work, now did it? Okay, if I make it a little bit too long and I drop it, ooh! Okay? And if you break the egg, what happens? What kind of grade do you get? 5 out of 10. And if it's kind of a crunch, it's a concussion, it's a 6 out of 10. And there's some of them you can hear where it just barely goes, ooh, ooh, ooh. Check it. Is it cracked? Maybe it'll have a teeniest little crack or no crack, and that's a 7 out of 10. Remember, when you're bungee jumping off of a bridge and you're going head first, do you really want to have your head go so other people can hear it? Probably not. Okay, so you want to get really close, but you don't want to be banging your head. So what you want to do is you want to figure out, gosh, what length do I use on this thing so that when I drop it, it comes really close, ooh, but it doesn't quite hit. Okay, now with that said, let's go back to the question. Do you want to make the rubber bands a little bit too long or a little bit too short? A little bit too short, because if they're a little bit too long, what happens? Omelets, right? Okay, so right about there looks to be about the right height. Okay, almost hit. But if I make it just a little bit longer, and then I drop it, so we don't want things too long, do we? If anything, you want to err on the side of being a little bit too short. So would you prefer 8 or 9 rubber bands in this situation? 8. But 8 is almost a whole rubber band too short, isn't it? I mean, that's going to be like 6 or 8 inches off the mark. So we got to find, you got to find something between 8 and 9, but you're not allowed to cut the rubber bands. I'll just make a passing comment. In the past, sometimes people have taken a rubber band and tied it so that it's only half of its normal length. So they have 8.5 of them, or they try and get a little fancier and do 8.7 of them. Okay? What you do is up to you. I will say nothing. Okay? I don't want to be involved, whether it's a fantastic jump or an omelet. I don't want to be either credited or blamed with whatever happens. Okay? It's all your group's decision. That way the grade is, whoa, if you want at least an A, which is a 9, you have to be within how much of the ground? You got to be within this far. You can't be any further off than that. Does it make sense once you get your height, how you can plug it into the equation to figure out how many rubber bands to use? Now, once everybody gets things figured out, we'll jump them in front of class, one at a time. Are you allowed to do practice jumps back there while you're waiting? No practice jumps. Because when you bungee jump off a bridge, they give you 2 or 3 practice jumps to see if it's going to work or not, or is the first deal it? Okay, the first deal's it. So no practice jumps. If anybody's caught practice jumping, you go to a grade of 5. Even if it didn't hit the ground. Okay? So what'll happen then is up here at the front, while you're doing that stuff, I'm going to mark this off, and like here would be maybe 4 feet. Right around here would be 5 feet. Right around here would be 6 feet, and they'll be marked off by the inches. Okay? And what you do then is once you turn, you come up with your meter stick, put the top edge of the meter stick even with whatever the jump height is. Not the bottom edge, the top edge. Because that will ensure then that when you hook the rubber band over, that this top edge of the meter stick is the height from which you really drop it, won't it? If you do the bottom edge, is that going to make what's that going to do to your clearance? Is it going to give you more or less clearance on the ground? Well, let's see, it was here, and now you move the stick up, and as you move the stick up, does that give you more or less room? Well, you're moving it up, so you're moving it away from the floor, so as you it's going to give you more, isn't it? So it'll be more clearance, but more clearance may be a good or a bad thing. Okay? The other thing to be careful of, and I've seen groups do this, they've got the meter stick out, and I'll try and caution folks about this, but they get the meter stick out, and then instead of having it come straight out, they let it kind of start doing this. And you don't want to jump back here up against the board. Why not? Because when the egg comes back up, it's going to go boink, and you've got a mess. So you want to be out here, like here, a couple of tiles out. And we'll have somebody's cell phone running in slow motion so we can do a instant replay and see what the deal is and get grades. Does that make sense to everybody, what's going on Friday? If you're not quite sure, you can watch it on YouTube. There's a bunch of them, bungee jumping eggs, or the bungee egg project or something like this. I've done this for a lot of years, and folks love this. It's fun. It's kind of a cool day. see Friday, won't we? Okay, please. Oh, I thought somebody said something. I'm sorry. Okay. Are you good? Is this making sense? Okay, so Friday when you come in, there will be meter sticks, there'll be eggs, there'll be the netting, rubber bands, paper clips. When you do your data, just take 3 rubber bands. You're only allowed to jump with 1, 2, and 3 rubber bands. Okay. Do the regression analysis, either on your calculator or Desmos. Get your equation. By then you'll have your height. Plug the height into the equation. Come up and get that many rubber bands. And then it'll be jump off time. Okay. And an extra point to the team who comes closest without hitting. Yes, sir?
Are we taping the pen to the meter stick?
If you want to, what are you hoping to accomplish with it?
Like, so would we have to hold the pen while we...
Oh, you're allowed to, yeah, you can hold. What's going to happen is when you're up here, somebody's going to hold the meter stick. So somebody in your team's going to hold the meter stick. And you're going to have the rubber band looped over the meter stick, and there'll be a second person holding it by the paper clip and doing the bombs away.
Yeah, that's what I mean. I mean the pen. So is this
Okay,
gonna be...
there won't be a pen. There'll be the meter stick and then somebody.
Oh, okay.
Okay? Now, when you are at your desk, the meter stick's going to be like this, and you may want a pen or something to bring out so that you're jumping from out here, because you don't want to be right up against the meter stick because the egg will go down and it'll bounce back up, and I've seen them bounce into the meter stick. And you're dead before you even get to the bridge. Okay? Make sense to everybody? A lot of them on YouTube use plastic bags, but I think that's kind of the wimpy way out. Okay. Okay. Everybody good with that? You've got this information. It'll give you a little something to read through. Do you see here in the middle where it says exploring your model? One or more of those questions would be a real fair question for the test. Questions like, what does the constant in your equation represent? Now, one of the things you're asked to do is you're going to have your paper clip, your netting, and your egg. And you're asked to measure this distance from the top of the paper clip to the bottom of the netting. Be sure to measure that distance. Jet propelled egg. Okay? So measure this distance. Be sure to do that. It's easy to get into the other stuff and forget about that. But be sure you do that.
Also, we got to measure the distance of
Right. After you get it all put together, just go ahead and measure that distance, because that'll help you to answer this stuff on exploring the model. Okay? And we'll talk about that next week. Because Friday's going to be a very busy day. Okay? Friday, when you walk in, and you may want to figure out who your team's going to be today, so that Friday when you come in, you're on it. And I don't care if you come in early. Okay? I'll get over here as fast as I can from the other room and get stuff put out as fast as I can. Okay? So, it'll be fun. We'll get it figured out somehow or another. Okay. Let's take a look at what's going on with this other stuff. We were in section 2.4. We were talking about modeling, which is what this egg jump thing is, isn't it? We're trying to use an equation to model what happens with the rubber bands. Okay? So, we're talking about modeling. We had talked some about things like if you've got this 100-gallon tank. Remember we did that the other day? It's 100 gallons. And it leaks at a rate of, what did I say, half gallon a minute? And asked how long would it take for it to go dry? Well, if it takes a half a gallon per minute, how long would it take for that tank to just run dry without any cows or anything drinking out of it? 200 minutes? Okay. Yes, sir.
An hour and 40 minutes.
Okay, well, I've changed it a little bit this time. Because this time, I think last time we drained halfway.
Wait, oh, where are you going to now?
Okay, I think before we drained halfway, which would have been 100 minutes, which would have been an hour and 40 minutes, which is spot on. But this time I asked how long till it goes empty, which is 200 minutes. Uh-oh. And if you're talking to somebody on the phone or texting, hey, I'll see you in 200 minutes. Really? So 200 minutes is, 3 hours and 20 minutes. Now, does that make sense to the rest of you where that number came from? Or is Samantha in a team all by herself and everybody's just saying, I don't know where it came from, but I guess I'll miss it on the quiz and Samantha will get it right. Are you okay with where that came from? Okay. So I don't want to bore you either. All right. Let's say we have something like this. Some things are what are called piecewise defined functions. Piecewise defined functions. My son plays hockey. He plays goalie. There's no place around here that sells hockey equipment, especially goalie equipment. The closest places are Columbus and Indianapolis. And then the next closest is Cleveland. And then you finally get into hockey territory. So what we wind up doing is we go to a couple of websites like goaliemonkey.com and we order stuff. Now, part of the price of ordering is the cost for the shipping, isn't it? When the stuff is shipped, okay, we can order a variety of different things and they all ship at the same price and the price fluctuates. What controls the price of it, basically, for shipping? The weight, isn't it? How far it travels, how much weight there is to it. Those are a couple of the parameters. Size comes into play, but then it starts to get too crazy. Now we've got 3 variables, don't we? Remember I mentioned the other week that, it's real easy to get more than one variable? Whoa, we're just talking about trying to ship some hockey pucks, and we're already into 3 variables. Weight, size, distance. Oh, a 4th one, how much time are you willing to wait for it? Ah, yeah. Now we're up to 4 variables. And then the cost would be a 5th. And we're in trouble because you can't graph in 5 dimensions, can you? Okay. But let's back this off a little bit and we'll just focus on the weight. Acknowledging that the others exist. Yep, they do. But most of the time, stuff just pretty much runs on weight. I guess they just kind of average it out over a zillion packages. When UPS, FedEx, USPS, or whoever is shipping that item bills them, how do they figure out how much to charge? Well, we talked about all those things, but we'll just go with the weight. And let's say that on one order, we order 5 pucks. Do all pucks have the exact same perfect weight? They're just wads of rubber, okay? So if we order 5 pucks one time, and later on order 5 pucks, and this one weighs slightly more than this set did, do they charge slightly more for the shipping? No, they charge the same price because it's just slightly more. So what they do is they kind of take things in groupings. If it's between this weight and this weight, we'll charge $5. Okay? And what can wind up happening is that you get different weight ranges all going to the same price. So for example, it might be $5 shipping if it's from 0 to 10 pounds. I'm just making up some numbers here. $7 shipping if it's more than 10 pounds but less than or equal to 20 pounds. $9 if it's more than 20 pounds but less than or equal to 30 pounds. And you get the idea. So $11 if it's more than 30 pounds but less than or equal to 40 pounds. So if you buy some stuff and it weighs 26 pounds, what's the shipping on it going to be? $9. A couple of years ago, we bought him 50 hockey pucks for part of his Christmas present. It's kind of funny. We just shoved hockey pucks in with everything else, and everything he opened, you know, he had some pants for Christmas, and every pocket had pucks jammed in it and stuff. Geez, already more pucks? Okay. It was kind of heavy. And let's say it weighed 37 pounds. How much would shipping on it have been? 37 pounds. $11. Okay. When you graph something like this, you graph it with the weight, because the weight is going to decide the cost, right? So the weight would be the horizontal, the x, and the cost is going to be over here. So we'll have our 5, 7, 9, and $11 there. Then our weight is going to be 10, 20, 30, and 40 across the bottom. Well, gosh, how do you graph this? If it's more than 0 pounds, which is what anything would be, even if it's just a mouth guard, okay? If it's more than 0 but up to 10 pounds, the cost for shipping is $5. So the cost for shipping would start at an open dot all the way over to 10. Anything in that price range, $5. Does that make sense? Okay, as soon as you get over 10 pounds, the shipping weight goes up to 7. And it stays at all the way up to 20 pounds. Then, if you're more than 20 pounds, all the way over to 30, $9. Then the last thing, if you're over 30, and all the way over to 40, $11. This is what a piecewise function looks like. It's also called a stepwise function because it looks like it's a whole series of steps. Okay. Does that make sense to everybody? There are functions that behave like that, and I just want you to realize that those things really do exist. Hurricanes. Here's a question for you. Are there more or less total hurricanes occurring each year than 30 years ago or 50 years ago? Actually less. Are there more or less tornadoes occurring now than there were 50 years ago? Curiously, actually less. Well, wait a minute, Chuck, this stuff with this global warming, doesn't it say everything should be increasing and getting worse? Well, it does, but that's just a theory, and the data doesn't always fit it. Interesting. I'll make one other comment. The sun goes in cycles where sometimes it's hotter than other times. What's something you think that would have a real impact on the Earth's temperature? You think maybe the sun getting hotter would have some impact on the Earth's temperature?
Is that why it's like a million degrees in September? Is that why it's like a million degrees in September?
No, that has to do with more local things. What the temperature of the sun would have to do with is the overall trend. Is the overall temperature going up or going down? Okay? Yeah, it feels like it sometimes here in September. Holy mackerel, worse than August. I'll throw this out as a thought too. Cincinnati. Has it always been this temperature here? What did it used to be? Used to be cold. Used to be a glacier, didn't it? Yeah. There used to be about a mile thick layer of ice here in Cincinnati. What caused it to melt? There weren't any. Global warming caused it, right? Now the question is, how many cars were there around and how many factories were there around then to cause global warming? Oh, so the warming occurred by something else, didn't it? Okay, before there were glaciers. What kind of fossils are there around here? Have you ever seen the fossils around here? Oh, you need to get out more. You know what shape all the fossils around Cincinnati are? Seashells. Get out of here, Chuck. Really? Yeah, they're seashells. They're Ordovician era seashells. It's one of the few places, in fact, the only place in the world where you can find fossils from that age. People from all over the world come here for our fossils. Really? Yeah. Well, wait a minute. There was a mile thick layer of ice, and before that, what was it here? How would we get seashells? Okay, before the glaciers, back a good chunk before that, this was like Hawaii here. This was shallow ocean. Shallow, warm ocean. I'm just throwing some thoughts out there. I'm not asking you to change anything that you may be passionately involved in, but I'm saying there is some interesting evidence and suggestions out there that maybe it reaches beyond just us. The sun goes through cycles. I know some of this stuff you've never heard because it's not politically correct. Okay?
Oh, it's true.
Okay? I'm not saying it's true or not. I'm just saying that there's some interesting other evidence out there, and if you do much digging around, you'll find some other interesting stuff. Anyway, piecewise functions. They go in steps. Where were you going with that stuff with tornadoes and hurricanes anyway, Chuck? Well, how do they measure the severity of a tornado? By how many trailers it tips over? By how many cows it blows out through the cornfields? No, by the speed of the wind. They measure the severity by the speed of the wind. And the wind speeds on them go something like this. On the scale, a tornado of 1 is between 40 and 72. A wind speed of 2 is 72. And you don't have to memorize this. Okay? I want you to just see that there really are stepped functions. 157, okay? And it's going up by about 40 every time, isn't it? Steps of about 40. So this 4 is going to be 157. Notice strictly less than. Okay, and it bumps up a little bit to about 206. And then the last one is 206 to 260. Okay. Yes, sir.
Has there ever been like a tornado recorded over 260?
You know, I don't know. I'm sure there has to have been somewhere sometime, but not too often. We don't want to see them around here. But if you graph this, do you see, first off, what's going to go on the horizontal axis, the wind speed or the scale number? You got 50-50, right? Which one controls the other one? Does the scale number control what the wind is in the tornado, or does the wind in the tornado decide how severe of a tornado it is?
The wind.
The wind does. Okay, so we're going to put the wind down here. and then a scale over here. Okay, and we have a 1, a 2, 3, a 4, and a 5. And this will do stuff like this again, where the wind speed's going to be like that. And they're called step functions. Step because it looks like a series of steps. Or piecewise function because there's a whole series of pieces to it. Does that make sense? Okay, some things are modeled like this with a stepwise function. Okay? Depends on what's going on. Some things are modeled with what is called a greatest integer function. The greatest integer function has its own notation, and this is around page 141, just in case you're trying to keep tabs of about where we are in the book. It's called the greatest integer function. Kind of an unusual looking notation for it. You may have seen it, you may not. It starts out with a bracket, but it has kind of like a double spine on each side of the bracket. Okay? So it looks kind of like that. It's called a greatest integer function. Now what these do is they return the value of the largest integer that's less than or equal to that x value. So for example, if y is equal to 3.01, what we'll get back is 3. If y is equal to 3.52, once again it'll return the integer part, 3. If y is equal to 3.99, what's its return value? 3. So where does this come into play? Well, in production. Let's say you're making refrigerators, microwaves, whatever it is. Okay? And at the end of the day, the total production quantity, let's use a Q here for quantity, number of units made is 274.6. If we're talking microwave ovens, if we're talking refrigerators, at the end of the day, how many refrigerators have been produced? 274. Why don't you round up? You can't sell that other one yet, can you? Come in the next day and finish it, put the compressor and the door on, stuff like that in it, and then you now have something you can sell. But greatest integer function allows you to count how many whole things are there that are ready for sale. Does that make sense? So depending on what you're trying to model, sometimes a greatest integer function will come into play. You can also run into scenarios where you have what is called a direct variation. With a direct variation, springs, not the kind that run water, but you know, the kind that stretch and come back and stuff like that. If you have a spring, and this is a classic experiment in physics, and put a little box on it, what's going to happen to that spring's length when you put the box on it? It's going to stretch out some, isn't it? If we put a heavier box on it, what's going to happen to the spring? It's going to stretch even further, isn't it? The amount of stretch that you get in the spring is directly related to the weight that you hang on it. No big surprise there, is there? Okay. This is what is called Hooke's law. Hooke is the physicist who came across this. Hooke's law. And what it basically says is the stretch length is going to be equal to some constant times the amount of weight that you hang on the spring. So y is going to be how far does it stretch. K is going to be a constant that tells you about how that particular spring behaves. Do all springs stretch at the same rate? No way. Have you seen those little springs that are inside of the retractable pens, you know, that you click, 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 click? Have you ever torn one of those apart? There's a little spring inside there, isn't there? Okay? And our kids would, if we weren't looking, grab them and go and pull them way out, and they wouldn't go back, and crud, dude, you just broke the pen. Okay? Does it take a whole lot of pull to pull that spring way out? Not much. Have you ever seen a spring on a car, underneath the car? They're usually about a foot tall and about 5 or so inches in diameter. Think one of our kids could grab one of those puppies and pull it way out? You think they could even get it to compress? That thing's not going to move, is it? It provides a lot more resistance to moving. The amount of resistance that it provides is this number for K. Okay? So y is going to be the length. K is going to be how resistant is the spring to stretching. And x is going to be the weight that you hang on it. So let's do an example here. We have some kind of a spring. Okay? And if we hang 2 pounds on it, the spring gives a total length of 12 inches. Okay? How far would the spring stretch if we were to hang 5 pounds on it? How far would it stretch with 5 pounds on it? Well, what we can do is we can back up and we can use the information that we have. We have this. We know that y is equal to k times x. Y is what's y? It's the stretch length. Then, so the 12 is going to go over here. Equals k. That talks about how the spring behaves. What's x talk about? Okay, yeah, the weight. Could we solve for k here? Yeah, k would equal what? 6. So this then gives us the equation y equals 6x. That was pretty easy to get that data or coefficient that describes the spring, wasn't it? So now that you have this, could you figure out how far that thing's going to stretch? Yeah, how far is it going to stretch this time? 30 inches, isn't it? Which is kind of neat, because if you have a spring, let's say a mobile or something like that, you're hanging up in a room, and you want it to stretch so that it just barely hangs above this table. And right now it has, 6 ounces on it. And with the 6 ounces, it comes down 2 feet. How much weight do you have to hang on it if you want this thing to come down so that now it's 54 inches? How much weight do you have to hang on so that this mobile or whatever it is hangs just above the table? Well, let's see here. 2 feet is equal to k times 6 ounces. What's k equal to? 2 over 6, which is a third. Okay, so now we have y equals 1/3 k. And this 54 inches that we want to hang down, is that the y value or the x value? It's the y value, isn't it? Okay, so we can put the 54 here, equals 1/3 k. K is going to equal to 3 times, so that's 162. Now be careful, this is in pounds, so you don't have to have somebody hanging off of it. 162 ounces. How many ounces are there in a pound? 16 ounces to a pound. So you'd have to hang about how much off of that spring to get it down there just above the table? 10 pounds. That's a lot of weight. That's a small bowling ball. Does that make sense how to make that computation? Are you okay? I'll get some homework posted for you. We'll fiddle with those on paper till I can get some going on my math lab. Folks, I hope you have a good day. I look forward to seeing you Friday.